Now we're going to look at the ionization energy trend. This is the energy required to remove an electron. Remember, removing electrons is when you make cations. Now, these charts and the other charts will have numbers on them. We don't want you to go and look back at these charts and look at the numbers and compare the numbers. The idea behind trends is that you have a periodic chart already laid out for you. And so if you know the direction of the trend, you can make predictions. There's like one exception that we expect you to know. And besides that, we're not stressing about every itty bitty little detail. So make sure you keep in line with the trend. So in this case, you can see that 2370 is much, much smaller than like 3850. So this is where you have a high or a large ionization energy, and this is where you have a small ionization energy. Now, what does this mean? If you have a high energy, what that means is that if you think of energy as money, it means that you're going to have to pay helium this much money for him to give you his electron. Or you're going to have to pay neon this much money. You'll notice all these noble gases, they've got really high, steep prices. That's one of the reasons why chemistry with those elements just doesn't happen very much. The elements aren't willing to sell off their electrons. And you'll notice as we work our way over here on the chart, these elements become more and more willing to sell their electrons for low prices. We care about this trend because if you have a low ionization energy, then you're an element that's willing to give up an electron. And it makes sense that this side of the chart wants to give up the electron because we know that's the side of the chart that wants to go positive anyways. Why would it be that these noble gases don't want to give up their electrons? It goes back to the idea of them being fully filled. So for neon, remember, he is just like that. He's fully filled. He doesn't want to give it because he's at 8, he's all the way filled. He doesn't want to give it up and become unstable in any way. You'll notice that fluorine's value, again, he's only, if you draw fluorine out, he's only 1 electron away from being stable. He doesn't want to give up this electron to someone else to have to go and find more electrons to be stable. He wants to gain an electron. That's why these values in here are so high for these guys. They're so close to being at 8. And here's another visual for the chart. So you can see again, it's going in that direction. It's kind of slightly rotated oddly. So here's helium, he's over here. So it's kind of rotated, but that's just another visual on the chart to help you out. And you'll notice the transition metals kind of sort of stay in the same-ish range. That's the way the D block does. So ionization energy, you can do more than just lose 1 electron. We just did an example in aluminum up here, where aluminum lost 3 electrons. That would have been his 3rd ionization energy. His first was losing 1 of those, and then his second, and then his 3rd. Each time you lose an electron, it takes more and more energy to remove subsequent electrons, unless you are doing something that makes the element happy. When we got to this state right here, all of a sudden our aluminum was fully filled. So we had our P electrons there, and our S, that's 3. That's what he looked like. So when we took off those 3 electrons, our P and our 3s's all disappeared, and he got to go back to that state with his 2p electrons all being filled. I drew that one funny. So he's sitting at 8 here. You can go back and count them if you're not sure. So each subsequent pulling off of electrons will take more and more energy. But note that if you're doing something that the element wants it to do, which is somehow getting it to 8, then you're going to have a drop in energy. So here's the big question. Why does this happen? So here's one of our exceptions here. You'll notice too, like the number of electrons, like the closer the electrons are, the more likely you are to have some weird little funny things happening. Notice these trends are a little bit smoother. So why does oxygen do that little dip? And why are these so very close? Even those are quite close, right? So why is it so close? Let's look at the difference between oxygen and neon. Sorry, nitrogen. Oxygen and nitrogen. Remember, this is losing electrons. When we lose electrons, we write them as a product. Our equations never have minus signs in them. You don't write aluminum minus an electron goes to something. what you do is you say that it's a product on this side. So this is what this means by losing an electron. It's a product. It's going to go somewhere else. So oxygen, when he loses an electron, the one he's obviously going to lose is this one right here. He will become this. Remember, oxygen is a lower energy. You would expect it to be this, NOF, like that. But when oxygen loses, he goes and he becomes half full. Now you go ahead and fill in what happens with nitrogen. You can pick any of them. And then this is the one that's half full. So the reason that this changes order and it becomes ONF is because this one, when you do ionization energy, this one becomes half full. And this one stops being half filled. So this is becoming more stable. And this one is becoming less stable.